Welcome to today's paper reading. Today's paper is titled, Machine Unlearning in Generative AI, a Survey. This paper, published in the Journal of the ACM, surveys the topic of machine unlearning in generative AI by Zheyuan Liu and colleagues from the University of Notre Dame and the University of Pennsylvania. The abstract introduces a scalable and clear method to measure the reliability of models in accurately recognizing image content. This reliability measurement is crucial for ensuring the accuracy and trustworthiness of generative models. In the context of safety alignment, generative models can benefit from unlearning techniques to mitigate the influence of undesirable data while preserving their utility for relevant tasks. This is particularly important for reducing the generation of inappropriate content. For privacy compliance, unlearning approaches help in safely removing sensitive data upon request, ensuring compliance with privacy legislation such as the right to be forgotten. Table 1 provides a comprehensive comparison of existing surveys on generative machine unlearning. It highlights the key aspects of unlearning objectives, setup, and frameworks. The table categorizes the surveys based on their focus on accuracy, locality, and generalizability of unlearning techniques. It also outlines the different setups and frameworks used in these surveys, including applications in generative AI, Gen AI, large language models, LLMs, generative image models, and multimodal large language models, MLMs. This comparison serves as a valuable resource for understanding the current state of research in generative machine unlearning. Figure 1 illustrates the problems faced by contemporary generative models across different scenarios. These models, which are designed to create new data instances that resemble a given training dataset, often encounter issues such as bias, hallucination, and privacy concerns. The figure categorizes these problems, highlighting the challenges in ensuring that generative models produce accurate, fair, and secure outputs. By examining these issues, the figure aims to guide future research and development towards more robust and reliable generative models. Figure 2 provides an overall assessment of 3 critical dimensions in the context of harmful unlearning for the Llama 2-7B model. The accuracy and generalizability metrics are derived from the model's safety rate after applying various unlearning approaches such as GA plus mismatch, skew, and task vector. The preserved knowledge dimension is represented by the massive multitask language understanding (MLU) benchmark, which has been normalized to ensure consistent comparison with the other metrics. This figure is crucial for understanding the effectiveness of different unlearning techniques in maintaining model performance while ensuring the removal of harmful content. Figure 3 illustrates the different types of generative models. These include generative image models such as autoencoders, generative adversarial networks, GNs, and diffusion models. Language models, which include both probabilistic models and large language models, LLMs, are also depicted. Additionally, multimodal, large language models, MLLMs, that integrate information from various data modalities are shown. This figure provides a comprehensive overview of the diverse categories within generative models. Table 2 provides a detailed comparison of various unlearning strategies across 3 key metrics: accuracy, locality, and generalizability. Each strategy is highlighted where it excels, indicating its strengths in specific areas. For instance, gradient-based strategies with reverse loss are noted for their high accuracy, while data sharding strategies are particularly strong in locality. Task vectors, on the other hand, demonstrate high generalizability, making them versatile across different contexts. This table serves as a valuable reference for understanding the performance characteristics of different unlearning methods. Table 3 categorizes representative machine unlearning (MU) approaches for generative AI, Gen AI models, distinguishing between parameter optimization and in-context unlearning strategies. The table highlights various unlearning applications such as safety alignment, hallucination reduction, and bias/unfairness alleviation. It also lists the generative backbones used in these approaches, including Llama 2/OPT, T5, and diffusion models. Each approach is associated with specific references that detail the methodology and results of the unlearning techniques applied. Table 4 provides a summary of datasets commonly used in the field of generative AI for machine unlearning (MU) approaches. These datasets are categorized by their intended unlearning objectives, such as safety alignment, copyrights protection, and hallucination reduction. For instance, datasets like civil comments and PKU Safe RLHF are used for safety alignment, focusing on toxicity and harmful content. The Harry Potter and book corpus datasets are employed for copyrights protection, aiming to eliminate specific content generation abilities. Additionally, datasets such as HallyVal, Counterfact, and Truthful QA are utilized for hallucination reduction, ensuring models do not generate misleading or incorrect information. Each dataset is accompanied by its task type, generation or classification, and the number of instances, providing a comprehensive overview for future MU research. The introduction of this paper focuses on the concept of machine unlearning within the context of generative AI. This includes the unlearning of specific information in large language models, LLMs, and the use of gradient-based weight saliency for selective forgetting in deep networks. The paper also explores the applications of generative AI, such as text-image generation and concept editing in diffusion models, which personalize these processes. Additionally, the paper addresses privacy and security concerns, discussing data deletion in machine learning, the preservation of patient privacy, and methods to avoid copyright infringement. In this section, the methodology focuses on a learning approach to forgetting within deep generative models, as presented at NeurIPS 2024. This approach is influenced by the work of Jonathan Ho, Ajay Jain, and Peter Abiel, who introduced denoising diffusion probabilistic models in 2020 at NeurIPS. Additionally, the method considers data protection issues, referencing the work of Chris J. Hoefnagel, Bart van der Sloot, and Frederik Zuiderveen Borgesius on the European Union's General Data Protection Regulations in 2019. This section of the paper surveys various techniques for machine unlearning in generative AI models. Key techniques include parameter-efficient transfer learning, low-rank adaptation, and model deficiency unlearning. These methods are applied to address critical issues such as privacy protection, mitigating bias, and enhancing model safety. However, the implementation of these techniques presents several challenges, including the need to balance efficiency with effectiveness, ensuring a proper balance between privacy and utility, and maintaining robustness against adversarial attacks. In the related work section, the focus is on machine unlearning within generative AI. Specifically, the discussion revolves around diffusion models and large language models. For diffusion models, the research highlights the challenges of safety-driven unlearning and the persistence of unsafe image generation despite unlearning efforts. The Unlearn Canvas dataset is introduced as a benchmark for evaluating machine unlearning in diffusion models. In the context of large language models, the studies explore the learning and subsequent forgetting of unsafe examples, examining how these processes affect model performance. Lastly, a survey on machine unlearning provides a comprehensive overview of current research, identifying key findings and trends that guide future directions in the field. In this conclusion, the authors discuss the survey of large language models, LLMs, as documented in the AR14 preprint 2303.18223. They highlight the work on judging LLM as a judge with MTBench and Chatbot Arena, which is set to be presented at NeurIPS 2024. Additionally, the authors reference the research by Zhou et al. On making harmful behaviors unlearnable for LLMs, as detailed in the AR14 preprint 2311.02105. The future directions of this research include further exploration of these benchmarks and the focus on making harmful behaviors unlearnable. Thank you for watching.